We have a sample problem here. You are in a 24 degrees Celsius room listening to your roommate practice the violin. As one note is played, you hear a note with a wavelength of 60 centimeters. If the vibrating section of the 1.3 grams per meter violin string has a length of 40 centimeters, what is the tension in the string? Okay, we have two separate things going on here. You are hearing, meaning there's a sound wave that you are listening to. That sound wave depends upon this temperature of the room. The sound wave, though, is created by your roommate practicing the violin and thus drawing their bow across the string of the violin. So we have a sound wave and a wave on a string. They are not going to have the same speeds necessarily. In fact, just assume they do not have the same speed because they're totally different types of waves. But they will have one thing in common. If we think about the string itself, a stringed instrument, when you draw the bow across it, as a violin, for example, that string is going to be vibrating back and forth and back and forth. As it vibrates back and forth, it's pushing and pulling on these air molecules. And so we're getting compressions and rarefactions and compressions and rarefactions. The oscillation of the string is what is creating the sound wave. So the only thing these are going to have in common, the wave on the string and the sound wave, will have the same frequency. Because however fast the string oscillates back and forth is how fast it causes the air molecules to have, not fast as in speed, the oscillation rate. So that however vibrating frequency is going to be the frequency it's oscillating the air molecules at. So that's all they have in common. We're trying to find the force of tension in the string itself. And as I have mentioned before, the fundamental, we can always assume a stringed instrument plays the fundamental frequency, unless the problem specifically specifies something else. And so the equation that will apply to the string, this fundamental frequency, will be 1 over 2L. L is the vibrating section of the string. So in reading the problem, it's telling us the vibrating section of this string has a length of 40 centimeters, which we will want in meters. They've also given us the linear mass density of this string, the 1.3 grams per meter, which we will want in kilograms per meter. We want the force of tension. This is what we want to find. We have L, we have mu. We're going to need to figure out the frequency before we can solve for the tension. We can certainly get symbolically to the force of tension first. I bring the 2L over. If I square both sides, so square this, that will leave me with the tension over mu. So I can bring mu up. So I'm ready to solve for tension. I just need to know this frequency F1. And that's where the sound is going to come into play. We're told we are in a 24 degrees Celsius room. So the temperature in degrees Celsius is 24 degrees. We're also told that we hear a note that has a wavelength. So the wavelength of this sound wave is 60 centimeters, or 0.6 meters. All right, so sound, we know the speed of sound depends on the temperature. This was in our previous chapter. So we can calculate this. If I go ahead and put my 24 degrees in for this this temperature. See, there's too many T's here. So T with those parentheses of degrees Celsius is our temperature. Putting that in, I'm finding a speed of 345.24. I'm keeping a few digits out because I'm not at a final answer. So now I have the speed of specifically this sound wave. The problem gave me the wavelength of this sound wave. And I know for every type of wave that the speed is equal to wavelength times frequency. So even though wavelength and frequency don't determine the speed, I can certainly use this relationship to find one value if I know the other two. So the frequency of the sound wave that we're listening to will be the speed of the sound wave divided by the wavelength of the sound wave. So we have our speed, our wavelength of 0.6 meters. I need the wavelength in meters so that I'm coming up with hertz on the frequency. So I divide that by 0.6, and I find the frequency to be 575.41 hertz. The meters canceled, and so I'm left with 1/seconds. This frequency is the same. So the frequency of the sound wave I'm listening to is also the frequency of the wave on the string. So now I can plug in these values to the length of the vibrating section. So again, the length of the vibrating section of the string, which we mentioned before, but I wanted to mention again. That's 0.4 meters. This frequency we just figured out. All of this needs to be squared, and then we multiply that by our linear mass density in kilograms per meter. Units, we end up with, in here, the meters squared over seconds squared from the hertz. We multiply by kilograms per meter, so one of the meters cancels. We'll have kilograms meters per second squared, which is a Newton, which that should be expected since we are solving for a tension. So now let me go ahead and plug this into my calculator. And then, so I'm getting 275 newtons. Technically, we have two significant figs, so this would be approximately 280 newtons. Would be the tension in this particular string.